This video has differential calculus topics, and remember you can subscribe to the Teach Quant YouTube channel. And a number of topics that we're going to consider in this video. The first one is the properties of limits. The second one is how to find the limit of a function, followed by how to differentiate, differentiation by product rule, differentiation by quotient rule, how to differentiate using chain rule, how to differentiate a parametric equation, application of differentiation, how to find stationary points, and we compare how differentiation and integration differs or how they are related. So these are the 10 different videos that have been combined together so that we can have one video for what you would call differential calculus. So I hope you'll enjoy the videos. Properties of limits, and we want to look at some examples. Assume that limit as x tends to a of f of x is equals to 4, and limit as x tends to a of g of x is equals to negative 3. For example, if we have been given limit as x tends to a of f of x plus g of x, according to the properties of limits, this is limit as x tends to a of f of x plus limit as x tends to a of g of x. And we know that limit as x tends to a of f of x we have been given as 4, and this one we have been given as negative 3, and that gives us the answer to be equals to 1. Another example, limit as x tends to a. This is now where we have a quotient. This we can write it as limit as x tends to a of the square root of f of x divided by limit as x tends to a of g of x. And that basically takes us to the square root of 4 all over negative 3, which is negative 2 over 3. Limit as x tends to a of 2 g of x will be equals to 2 limit as x tends to a of g of x, which is equals to 2 times negative 3, which is equals to negative 6. The fourth example, limit as x tends to a, the cube root of f of x minus g of x is equals to limit as x tends to a, f of x minus g of x, everything raised to power 1 over 3, which will basically be equals to limit x tends to a of f of x minus limit as x tends to a of g of x, everything raised to power negative. And we know that we have been given the limit of f of x and g of x, so this is 4 minus 3 raised to power a third, which is 7 raised to power a third. To find limit as x tends to 2 of 2x squared minus 5x plus 4. This will be a direct substitution, so it will be 2 squared minus 5 times 2 plus 4, which will be 8 minus 10 plus 4, which is to be 12 minus 10, and the answer will be equals to 2. Limit of a function. And basically, we want to look at a number of examples. And one of them is limit as x tends to 2 of 10, and that basically remains as 10. What about limit at x tends to 2 of x? It will give us 2, because what are we doing? The idea behind what we are doing is if we look at limit as x tends to a constant c of f of x, then it should be f of c. So we replace the f of x with c, what we have done in that example, and that's how we would get the limit of a function. And that means if we have another example, and in this case I want to get a limit as x tends to 3 of x squared plus 1. Basically, this will be 3 squared plus 1, and that will give us 9 plus 1 is 10. What about in cases like limit x tends to 4 of 4 over 4 x squared? That will be 4 over 4 squared, and that will give us 1 over 4. Example number 5. If I was to get the limit x tends to 1 of x minus 1 over x squared plus x minus 2. Now, you note that if we are to replace this, the elected will be giving me 1 minus 1, that will be 1 squared, plus 1 minus 2, which will be 0 over 0. And this is what we call as the indeterminate form. And so when we have indeterminate form, that's when we use what we call the L'Hopital's rule. And so what do? We differentiate the denominator and the numerator at the same time, and then we substitute. So I'm going to go through the problem again. So limit x tends to 1. So when I differentiate the topmost part, it will give me 1. And when I differentiate the lower part, it will give me 2x plus 1. And when I replace 1, it will be 1 over 2 plus 1, which is a third. So that's how I would approach that when I get the indeterminate form of the problem that I have. And that will apply in other cases. For example, a problem like the following we want to look at. If we look for limit as x tends to 0, if I was to substitute this directly, it will be sine 0 over 0, which is 0 over 0, which is again indeterminate. And since it is indeterminate, and then what do we do? So it is indeterminate. So what we do is we get limit as x tends to 0 over cos x over 1. And if you substitute, it will be cos 0 over 1 is equals to 1. So whenever you have the indeterminate form, then what we use is what we call the L'Hopital's rule. There are so many other examples we can think about. We can think about this, where, for example, I have, let me say it's infinity. So if I substitute this again,
it will be infinity over infinity, and the infinity over infinity is not known. So what we do is we go through the L'Hopital's rule again, and then it basically means then we need to differentiate 2x squared, which gives us 2x, and ex again remains as ex. If I substitute, I'll get 2 times infinity over e raised to power infinity. And again, that means we repeat the process because it is giving us indeterminate form. I also give you a problem, so it will be 2 over e raised to power x, and that will be 2 e raised to power infinity, which is 2 raised to power 2 over infinity, and any number. Remember that that 1 over infinity is equals to 0. So if you keep that in mind, then that would be the answer. So you note that we have differentiated this twice for us to get the limit. What about if we have other problems like, for example, this? If I said let's get limit x raised to x to 5, x over x minus 5. Now, even if we are to differentiate, even if we are to substitute, we'll get 5 over 0, which is undefined. So remember, this is not indeterminate because it is not 0 over 0. It is undetermined, undefined. So what we say is that limit does not exist. So that is something that we want to keep in mind, and we can go on and on and on using other approaches. We can think of other problems. I can give you maybe 2 more. So if, for example, I was to get limit as x tends to infinity of x squared plus x over x squared. Definitely, if you look at that problem, you realize that if I was to substitute directly, it will be infinity over infinity. So what I'll do is I'll be slightly clever, and I'll rewrite it in a different form. I'll write it as 1 plus 1 over x. And that takes me to 1 plus 1 over infinity. And that tells me that the limit for that would be equals to 1. I could have still used the L'Hopital's rule because infinity over infinity is also tricky. If I was to use the L'Hopital's rule, then it will be limit as x tends to infinity. I differentiate the power, the numerator, it will be 2x plus 1. I differentiate the denominator, it will be 2x. Then again, I go again and differentiate the second time. It will be 2 over 2. And definitely that one will be x tends to infinity over constant, just like our first problem. And that means then I'll stop at that point. So these are some of the examples of how to use limits. To consider a few examples, perform different types of differentiations. So if you are given an example of y is equals x cubed, so the first derivative of y with respect to x, which we can write as dy over dx, or you can write as y with a prime. What do we normally do? You take the power down, which is 3, and then you decrease the power by 1. So the answer gives you 3x squared. Want to get the second derivative, which I can also put down as y double prime, or if you wish, you can write it as dy squared over dx squared. So I'm going to differentiate the solution I got in the first step. So I put 2 down and I decrease the power of 2 by 1, and that gives me the answer as 6x. Again, The y prime, I'll write it as y prime, it will be 4. Then I'll take 4, and then I take the power of x minus 1. So that will give me 16x raised to power 3. And that would be the solution to that. Then we differentiate that. Now with that idea, I take 2 down and I reduce the power of 2 minus 1 gives me 1. I put 2 on the side. Remember, the power of x is 1. So it will be 1 minus 1. And there, literally what it means is I'm multiplying with x raised to power 0. Because what we know that any number to power 0 is always 1. And if you allow me, then I would put 1 down. I'll put x, and then I'll subtract by 1. So what am I trying to say? If I have a constant and I try to differentiate the constant, the answer is always 0. So this will be 2x. X raised to power 0, we have seen any number raised to power 0 is 1. So in the second part here, x raised to power 0 is 1, so it will be plus 2. And then here it will be 0 times 1 times x raised to power minus 1, and everything remains 0. So the first derivative of that polynomial would give us that. What we do is we take this and we differentiate. We take the power and then we differentiate. So it means then the first derivative will be equals to, when you differentiate x, you get 1. You put the 1 there, and then you multiply with the original function as it is. So the first derivative of e raised to power x remains e raised to power x. Again, you take the power, you differentiate, and this gives me 2x plus 1. So after I differentiate the power, so what is the solution? The first derivative will be equals to 2x plus 1. And then I write back the original function as it was. Then we take this, we differentiate it. So when we differentiate, then the solution becomes, after differentiating x, you get 1. And then you divide by original variable, which is x. So the first derivative of ln of x is 1 over x. So the first derivative, what do? We take 2x plus 1, again, this one. When you differentiate 2x plus 1, you get 2. After you get 2, then you divide by original function. So once you differentiate, you put the value there after you differentiate. After that, after you differentiate, you put the value there, then you divide with the original variable as it was. So that, and y prime is equals to cos x. That is, and then y is equals to cos x, and y prime is equals to negative sine x. So we consider the product rule method of differentiation, and I want to get the first derivative of that. So what does the product rule says? It says that I itemize my variables in terms of u and v. So what do? I differentiate u, I keep v constant, and then I keep u constant, and then I differentiate v. So in this case, I differentiate ln of x, which will give me 1 over x. Then I keep ex constant as it is. In the second case, I keep ln of x constant, and then I differentiate e of x. And when you differentiate e of x, we still have e of x. So that's the solution for my first derivative of that. So I could write it as that plus that. And that's the first derivative when I use the product rule. Another example I could think about when I'm using a product rule is an example of the form y is equals to x raised to power 4 maybe e raised to power 2x. Again, I separate it into two as u and v, and therefore y prime is u prime v plus u v prime, meaning u prime means the first derivative of u with respect to, so I'm referring to that as my u. So my y prime will be 4x cubed e of 2x plus x4 times 2e of 2x. And therefore, I can write this as 4x cubed plus 2x raised to power 4. And I could leave that as a solution to that product. And therefore, the first derivative is I differentiate sign, I get cos, then I multiply with cos x, and then I keep the sine x, and then I differentiate cos, I get negative sine x. So that would give me that, and you could go ahead and multiplying them out. Therefore, that will give me cos squared x minus sine squared x. So derivative, I want to differentiate this. The first part here, I have two parts, product rule. So the derivative of this will be 2x times 5, x squared plus 1 raised to power 4, ln of x plus x squared plus 1 raised to power 5 times 1 over x. And that gives me the derivative. Now, what have I done? The derivative of ln of x is 1 over x. The derivative of x squared plus 1 raised to power 5 is you take 5 down, you reduce the power by 1. That gives me x squared plus 1 to power 4. And then you differentiate what is inside the bracket. X squared plus 1, when you differentiate, you get 2x. So the first derivative of that, therefore I can write it as x squared plus 1 to power 4. And then 10x ln x plus 1 over x, x squared plus 1. Yeah, and you can simplify differentiation by quotient rule. And the general formula that we normally use is given by y is equals to u over v. So we assume you've been given an equation of that form. And therefore, the first derivative, the general formula that we use, so here we develop a formula, is we differentiate u, you keep v constant, minus u times the first derivative of v, and then we square the v. So we want to make one our u, the upper term to be our u, and the lower term to be our v. So mostly the quotient rule means you're dividing one function with another. So if my u is equals to sine x, the first derivative of u with respect to x will give me cos x. And if my v is cos x, then my v prime will be negative sine x. So according to that formula, then y, the first derivative of y is u prime, which is cos x times v, and that gives me cos squared x, then minus u and v prime. U and v prime is another minus sine squared x. And that's true. And then we know what is v. We know v is cos. So here, cos, then you square, it is cos squared. So you see here it's cos squared minus minus, which is positive. So cos squared plus sine squared is 1. That is a trigonometric identity over that. And therefore, the first derivative of tan x is equals to sec squared x, or is equal. Now, the trick I would have used here is I would have gone ahead and wrote it down like this. And from the knowledge that I have, I would have done this, and I would have gotten the answer as that, which is the same as minus 2 over x cubed. I could have done that from what I know. But I could also as well have used the quotient rule method. And so my u is 1, my u prime is 0. My v is x squared and my v prime is 2x. So my y prime would be u prime 0 times x squared minus 1 times 2x divided by x squared, which is minus 2x over x squared, which is x to power 4. And you can see already the solutions are equivalent. It's minus 2 over x cubed. So even if I use a quotient, all I could have done is directly, I would have come up with the same solution. Will be 1. My u prime will be 0. My v will be cos x. And my v prime will be equals to negative sine x. So that's what I would get. So what is the derivative of sec x? The first derivative of sec x will be u. It will be 0 times cos x minus u times v. And then you divide by cos squared x. And so that's what you get. And that's 0. That will be sine x all over cos squared x. So the first derivative of sec x is sine x over cos squared x, or if you wish, it could have been sec of x times tan of x. Because how did I know that? Remember, this is the same as sine x over cos x times 1 over cos x. And that will give me 1 over cos is sec, and then I have the tan. So u is ln of x, and u prime is 1 over x. So that's the first thing you have. And then we have v is equals to x squared, and v prime is 2x. So the first derivative of y will be u times u prime times v, then u times v prime, 2x times ln of x. And then everything we divide by x squared, which is our v, and then we square everything. So that's what we have, which will be x minus 2x ln of x all over x to power 4, which will be 1 minus 2 ln of x all over x cubed. And that differentiation by chain rule is the method we want to consider. So what we do is we let u be equals to x squared plus 2x plus 1. And therefore my equation changes to y raised to power 6. And now looking at that equation, I would not be able to look for dy dx. I would literally be looking for dy du. So for me to be able to look for dy dx, which is the first derivative of y with respect to x, I'll try to find the dy du, and then I look for the du, the dx. Now, if I differentiate dy with respect to u, I'll get 6 u raised to power 5. And then if I differentiate u with respect to x, I get 2x plus 2. And so that is what we call the chain rule. It makes it simpler for you to differentiate such equations. And therefore, my final solution becomes 6, 2x plus 2. And then we put back the u that we add. And remember, u is x squared plus 2x plus 5. U is x squared plus 2x plus 1 raised to power 5. And that gives me the first derivative of y with respect to x. Then I let u is equals to 2x plus 1. Therefore, my equation becomes y is equals to sine u. Why do we do this? To simplify the part of sine. Now it's only u. So if I'm going to try and differentiate, so I'll get dy with respect to u, and then u with respect to x. That's so. dy du, the derivative of sine x is cos, so it will be the cos of u for the first part, and the second part will be 2. So the first derivative, which is dy dx, the y prime, will be equals to 2 cos of 2x plus 1. And so what I do is I let u be equals to cos x, therefore y becomes e raised to power u. And again, therefore dy dx is dy du, because now y is related to u, times then du over du dx, because u is related to x. So, and that's the method we call the chain rule method. So if I differentiate the cosine, what do I get? First of all, dy du is e raised to power u, and then the du dx is negative sine x. So the first derivative will be negative sine x e raised to power u, and remember our u is cos x. Now, the same problem, we could have solved it, we could have decided to differentiate it without employing the use of the chain. And for those of us, we could have taken this, you differentiate it, and that will give us negative sine x. And therefore, you could have said that the first derivative will be equals to negative sine x, then e raised to power the original function. And you can see those two solutions are exactly the same. Parametric equation is what we want to look at. Given y is equals to cos 2t and x is equals to sine t, then we are told to find dy over dx. Now you'll see that y is represented in terms of t and x is represented in terms of t, but then we are supposed to find dy dx. And so dy dx, I can say it is the same as dy over dt, because we don't have a direct differentiation of dy dx and then dt all over dx. That's how we are able to link the two together so that we are able to differentiate. Now, what is the first derivative of y with respect to t? This is, we see y is equals to cos 2t. So what I'm going to do is I'll say y is equals to cos 2t. If I let u is equals to 2t, then y becomes cos u. Now, what am I interested in? I'm interested in finding the dy dt. So, dy dt is equals to dy over du times du dt. And we know that dy du is a derivative of cos, which is negative sine u, times du dt is 2. So that gives us negative 2 sine u. So the first part of dy dt is negative 2 sine u. And we know what is u? U is 2t. So dy dt will be equals negative 2 sine 2t. What about dt dx? Remember, what you have been given is x is equals to sine t. So the first thing is I'll have to look for dx dt. And the first derivative of x with respect to t is cos t. And therefore, dt over dx is 1 over cos t. From that, I just get the reciprocal. of that value that we got. So dy dx will be equals to dy dt times dt over dx, which is negative 2 sine 2t times 1 over cos t. So that would give me the solution to that first derivative of the 2 sine 2t divided by the cos of t. So that is a solution that you could leave it there. For some of us who are familiar with the double angles, we could have taken that problem to another level. And the level we are talking about is sine 2t can also be written as 2 sine t cos t. And so if I could write that based on the principle of the double angles or the angle identity, then dy dx can be written as negative 2 times 2 sine t cos t all over cos of t, which will give me negative 4 sine t. And that will give me the final solution. We have been given x is equals to 3t and y is equals to 9t squared. So the first part is to find dy over dx. Again, the procedure is the same. And what does that mean? So dy over dx is equals to dy dt times dt over dx. dy dt is 18t and dx over dt is equals to 3. And therefore, because we need dt dx, not dx dt, therefore dy dx will be equals to 18t times 1 over 3, which will give me the solution of 60 for that case, because we need dt dx, which is the reciprocal of what we found there. Find d squared y all over dx squared. Now, what does that mean? It basically means d squared y all over dx squared is to find d dx of dy dx. And that is find d dx of 60. Now, what is easier? I could use the implicit method, or I could say that since x is equals to 3t, then 2x will be equals to 60. I just multiply by 2. So whenever then there is a 60, then I'm going to replace it with 2x. That's basically what I've said there. So then I could say d dx. Instead of 60, I'll say 2x. And that should give me a solution of 2. That would be the answer for that. Now, if I wanted to use the implicit method, I could have said alternatively d dx of 60 will be d dt of 60 times dt all over dx. And you remember we got dt all over dx. We know that if x is equals 3t, then dx dt is a that. And therefore, I know that this will be d dt of 60 is 6, then times a that. And it would have still given me the same solution, just like the similar one that I have been able to get. The applications of differentiation, we have an example for a dosage of x cubic centimeters of a certain drug, the resulting blood pressure is approximated by Bx is equals to 305x squared minus 1830x cubed, and x lies between 0 and 0.16. So we are told to find the maximum blood pressure and the dosage at which it occurs. So that's differentiation. So we get the first derivative, which gives us 610x minus, if we multiply that, that becomes 5490x squared. B prime of x is equals to 0, and we want to get the critical point. And so if we do that, it basically means that 5490x squared is equals to 610x, and therefore x is equals to 610x over 5490x, and that gives us the value of x at 549. So this is our critical point. So the critical point occurs. So the critical point is at x is equals to 61,549, which is basically the dosage that we are talking about. Yeah, so we are told to find the maximum blood pressure and the dosage at which it occurs. So the dosage is that is the dosage because x is the dosage. Now let's find out if actually this is the maximum dosage that we can get. How do we get the maximum dosage? We test. So we are going to differentiate our B 2 times. We have differentiated the first time, and this time it gives us 610 minus 10980x. And when we substitute the value of x, 61 over 549, it becomes 610 minus 10980, 61,549. And this value will be equals to 610 minus 549 goes to 1098 2 times, so it will be 20 times 61, and definitely is less than 0. So then we know that Bx as a local maximum at that value that you've been given. X is equal 61,549. So to answer the question, the first part is the maximum BP, that is maximum blood pressure. That will be getting from the computations. It will basically be taking our Bx, our x is 61,549, and then we substitute it into this equation. Then minus 1830, 61,549 cubed. And so the maximum blood pressure will be 1.255. And then the second part is the dosage. The dosage is x is equals to 61,549. Moving body is given by the equation S is equals to 160t minus 16t squared. S is in meters and t in seconds. Find the body's velocity and acceleration as time t. So we know that velocity is given by change in speed with time. So that gives us the velocity, the change in speed with time, and that is what we have. And the velocity is given by meters per second. And then the second part is acceleration. And acceleration is given by change in velocity with time. And that gives us the acceleration. And it is in meters per second squared. And it's a negative sign because the object is decelerating. Parametric equations of a curve are x is equals to 3t over 1 plus t and y is equals to t squared over 1 plus t. We want to find the equations of the tangent and normal at the point for which t is equals to 2, which is dy over dx. Or if you want to put it in a slightly different way, it is change in y all over change in x. And we know that dy dx will be given by dy over dt times dt divided by the dx. Over dt, not dx, the dy over dt, one thing we need to find out is based on our equation, we are going to use the quotient rule. Our u is t, our u prime is 2t. And then our v is 1 plus t, and then our v prime is 1. So dy over dt is u prime v, which is 2t, 1 plus t, minus v prime divided by 1 plus t squared. And that's x over dt. Remember that our u is given by 3t. So our u prime is 3. We want to use the quotient rule to be able to differentiate. This is 1 plus t, and my v prime is 1. So my dx dt is u prime v minus v prime u. I think that's what we have. Divide everything by 1 plus t squared. And this simplifies to 3 plus 1 plus t squared. Now, we are looking for dt dx. dt dx will then be equals to 1 plus t squared over 3. And that takes us back to our problem that we had, which is finding the slope dy dx is equals to dy dt times dt over dx. And the first question is, what is my dy dt? My dy dt will be 2t plus t squared over 1 plus t squared, then times 1 plus t squared over 3. And that simplifies the equation to a form that gives me my slope of the line as 2t plus t squared divided by 3. And since I was told to find the value at t is equals to 2, this will be 2 times 2 plus t 2 squared divided by 3, which is 8 over 3. And that gives me the slope of the line of the tangent. First of all, I need to find the value of x when t is equals to 2. And that takes me to the equation of x, which is 3 times 2 all over 1 plus 2, which gives me the answer is 2. And then I look for the value of y at t is equals to 2. And y is given by 2 squared over 1 plus 2, which is 4 over 3. Now, y minus 4 over 3 divided by x minus 2 is equals to 8 over 3. So 3y minus 4 is equals to 8x minus 16. So 3y minus 8x is equals to minus 12 would form the tangent equation to find the normal. And we know that for us to get the normal, we know that negative 3 over 8 times 8 over 3 is equals to negative 1. So this forms the gradient when we are forming the normal, because for that to be then at the normal, then the product of the two should be equals to negative 1. And therefore, using the same points, y minus 4 over 3, x minus 2 should be equals to minus 3 over 8. And therefore, the equation to the normal, it will be 8y minus 32 over 3 is equals to minus 3x plus 6. So 24y minus 32 is equals to negative 9x plus 18. And so that forms the other equation, which is the normal equation. 24y plus 9x is equals to 50. The normal equation that we get. We look at the relationship between differentiation and integration. And basically what happens is that if you are given a function here, and this function, what happens is when you differentiate, what happens is that you get the first derivative. If you have been given the first derivative and you integrate it, then you get the original function, and this is basically part of the key lesson that we learn in calculus. Given your f of x to be equals to x squared, therefore the first derivative of that will give us 2x. So for us to get the original function, f of x will then be equals to the integral of f prime of x dx, and that is the integral of 2x dx. Of integration, so we'll get 2x squared over 2 plus c, which is x squared plus a constant. We want to look at the relationship. Number 2, we want to look at the relationship between tan x times sec x and sec x. So if we integrate tan x times sec x, we get sec x, and if we differentiate sec x, we get tan x sec x. So we can say then df dx will be equals to what? And we expect the answer to be equals to tan x sec x. Remember, your f of x, if I'm differentiating, I can write this as 1 over cos x, and this I'm going to use the quotient law. To 1, my u prime is equals to 0, my v is equals to cos x, and my v prime is equals to negative sine x. And therefore my df over dx is equals u prime times v minus sine x divided by cos of x squared using the quotient rule, which is sine x all over cos squared x. And that gives me tan x sec x. So the integral of tan x sec x dx will give me sec of x plus c. Just a constant of integration. So how do I do that? I'll take this and I'll write it exactly as sine x over cos x times 1 over cos x dx, and that will be the integral of sine x all over cos squared x dx. So I let u is equals to cos x, and I want to use a substitution method. Then I say du my dx is equals to negative sine x. And that means that my dx is equals to minus du all over sine x. And so that means then I can write the equation as sine x over u squared times negative du all over sine x. So what I'm sure about is that these two will cancel out, and that makes it easier for me. With that information, then what I have is a negative u raised to power minus 2 plus 1 divided minus 2 plus 1 du plus c. So, and that gives me 1 over u plus c. And we know what is 1 over u? 1 over u is 1 over cos x plus c, which will give me the sec x plus c. So I've shown that if I have a function f of x is equals to 2x all over x squared plus 1. So what happens to this variable? It's, it's, it is 2x over x squared plus 1. When I integrate, I get, and when I differentiate. So this is when you differentiate, and this is when you integrate. So that's what we want to show, that when I differentiate, I get that, and when I integrate, what do I get? So that we can link the relationship. So I'll start off with the differentiation. F of x is ln of x squared plus 1. So the df over dx will be equals to. So how do we differentiate the ln? You take this, you differentiate it, and this gives you 2x. So I'll put 2x there, and then I'm going to divide with the original function. And that is the rule of differentiation. So I've seen that if I differentiate ln of x squared plus 1, I get 2x over x squared plus 1. What about if I do the integral part? So if I integrate 2x over x squared plus 1 dx, so I let u is equals to x squared plus 1, and then du dx is equals to 2x. And what does that give you? And that tells you that my dx is du over 2x. So if I come back to my integral, I'll write it as 2x over u times du all over 2x. Again, we can easily see that that cancels. And if I integrate du over u, the integral, and this gives me ln of u plus c. And that is ln of u. My u is x squared plus 1 plus c. And that shows want to look at stationary points. And in the figure there, we can see that we have a point A, which we call the local maximum. We have the point B, which is the local minimum, and the point C, which is our saddle point. And the 3 points, point A, B, and C, are what we refer to as the stationary points. So given the function y is equals to x cubed minus 3x plus 3, find the stationary points. So we want to use the principles of differentiation to be able to do that. So one, find first derivative, and that basically means that dy dx is equals to 3x squared minus 3. And that we are going to equate to 0 to be able to solve for that. And this gives me the equation of the form 3 x minus 1 x plus 1 is equals to 0. Means that x is equals to 1 or x is equals to negative 1. When x is equals to 1, y is equals to 1 cubed minus 3 times 1 plus 3. And that gives us 1. So when x is 1, then y is equals to 1. And when x is equals to -1, y is equals to -1 cubed minus 3 times -1 plus 3. -1 cubed is negative. -3 times -1 is 9. 3 plus 3 is 9. So y is equals to -1 plus 3 plus 3, which is equals to 8. So we have our stationary points. One of them is when x is -1, y is 8. And the other one is when x is 1, then y is 1. So I wouldn't actually call them stationary points. I'll be calling them turning points, because we don't know, are they maxima, are they minima, or are they saddle point. So we use the second derivative to test the point. So the first is x is equal to -1. Then divide the d squared y over dx squared is equal to -6, and -6 is less than 0. Then that tells us that that point is a maximum point. If the second derivative in the second case is equals to 6, which is greater than 0, then this is what we call the minimum point. In the case that the second derivative would have been equals to 0, then that would have been a saddle point. So I have 2 points. I have a minimum and a maximum point. So those are the 2 points I have. One is a minima, and -1, 8 is a maxima. So with that information now, I can plot the graph. Now, based on the information that we have, I've been able to make a sketch whereby I have the 2 main points. I have my maxima point here, and I have my minima point here, and where the line cuts through the y-axis. And I've been able to make a sketch using that set of information. So that is the process that we normally take when we want to get the minima, the maxima, and the saddle points, or what we call the stationary points.